Hi, class. I hope you had a good holiday, had lots of candy, and were able to dodge the rain this weekend. I'm posting the solutions, and I thought I'd walk through things because I know we're both slowing down on the data manipulation piece, but now we're moving to the conceptually hardest section of the class. So I wanted to just go through all of the exercises and go through with a little bit more elaboration than I usually do. So I think we went through the data cleaning exercises in class, so we can just quickly go over that. We import our scores. We look at the underlying data. Let's just move this out of frame. We see that we have these math scores and that they're alternating such that we've got student one math score, then their reading score, so forth and so on. And we also have household income in this format. Parsing household income is pretty straightforward. We use this dstring command and let it know to ignore the letter K with this option replace so that it just makes this change in real time. For isolating these individual score components, what we do is we use this split command and we split on this underscore character. And because this format is pretty regular, we can just use this split to know that this is going to be the first part of the word, or first part you split on. This is going to be the second. SS in this case stands for sum score. And this third piece is a student's actual score. And so we go through, rename these objects to the relevant pieces. We have to convert this score component to a numeric value because it was part of a string. And we also have to, because strings are sort of persnickety to work with in Stata, you can't actually use them as features in a lot of models. Instead, what you have to do is encode them. And that's what we're doing here. So let's first do all of that cleaning. Okay, we didn't have any issues of note. And then we can start to do an analysis of, are these scores varying across class size? Note these consist of both math and reading scores right now. So there is that issue, but we're going to ignore that for now. And the thing that you should know about ANOVA, which stands for Analysis of Variance, is it's a fancy way of basically assessing whether or not there's a difference in means across groups. So in this case, instead of, say, running a t-test between large and small class sizes and small and medium class sizes and medium and large class sizes, what you can do, instead of having to worry about making all of those comparisons, you can see if there's any variation with respect to these outcomes across means, across these means. And that's all of what ANOVA is doing. And I'll post some supplementary slides on this because I really sort of breezed by it in class. But the basic idea is you are testing whether or not there are multiple means, if multiple means fit this data better. So in other words, estimating a mean for a small, medium, and large class size versus does it fit the data substantially better than just using one mean. So that's the basic intuition of that. And you're not going to see ANOVA in a lot of papers because the thing you should know about ANOVA is it's just a very specific form of regression. In addition to that, one of the things that you can also do instead of using this encode feature for generating data You can use tab and generate to also create lots of dummy variables. So whatever, so instead of using this tab slides code, you have these three variables that correspond to is class size large, is class size small, is class size medium. When you're working with really small data sets, or there aren't a huge number of categorical features, both of these approaches are equally useful. But particularly if you didn't spring for the really expensive Stata, or if you have just lots of variables, that having these one-dimensional dummy variables can get very expensive very fast in terms of computational time and resources. So typically, if all you're doing is regressing dummy variables, you don't necessarily need to have these permanent representations of is this class size small, medium, or large. But that's a bit of an aside. But what I did want to show you is that if you basically use this exact same model as our ANOVA with class size code, you get slightly different results because of how they're enumerated in variables, but the partial sum of squares and the mean sum of squares are identical, as well as the associated F and P values associated with that F statistic. So as you can see, they are identical, as well as the total sum of squares. That is probably the only instance in which you might prefer this tab generate option, so you can see this decomposition of, this is the explanatory value of a large class, this is the explanatory value of a medium class, whereas when we do it with this model formula, it assumes that these two categories are not as explicit. All right. Now, here is how I would do this problem, is instead I would use this IDOT notation, where it will tell me what is the effect of having where I regress score on all of the class size codes. And we know we have small, we have medium, but we don't have large. And so the way a regression works is that it typically codes things in terms of a reference category. You can actually exclude this reference category, and the way you would do that is by specifying no constant. Reg score class size code. See, I do it too. And actually, that's one thing I was unaware of, is that apparently, if you use this IDOT notation, it will leave out the reference category of large still, even if you use the IDOT notation. But if, say, for some reason you did want to note the individual associated effects, class size large, class size medium, class size small, corresponds to 1, 2, and 3. And these are the exact values of the means for those groups. And just to prove it to you, I sort score. You can see that it maps exactly to those values. But typically, what you will see more often than not is something of this form, And so you have to infer what the reference category is. So in this case, because we know small and medium are listed, the category that's not shown is going to be large. And the other piece that's useful to keep in mind is that that these formulas are additive. So we actually implicitly have a question of everyone gets this constant value, but whether or not you only get this addition of the small or medium coefficients if you're either small or medium. And we are going to go very carefully through these manipulations and how you can generate these predictions. But one thing I wanted to show you is that you can predict them explicitly with the predict command. And we're going to call this class size score overall. And what we can then do is we can look and we see that for all of our large class sizes, they correspond exactly to our constant. For our medium class sizes, it corresponds to our constant plus our medium coefficient. And for our small class sizes, it's our constant plus our small component, so 99.4 plus 10.92. So we can use that predict command in the future, and we'll talk a lot more about it next week, but I just wanted to demo it. Now, let's go through the exercise, the rest of the exercises. We need to reshape our data, save it, process it. And I think at this point, we've got a pretty good understanding of what our data looks like, that we've got 480 observations of individual students, and we have how big their class is, their household income, their binarized gender, and their associated class size, as well as their math and reading score. So the first question we asked is, what is the gender breakdown? Does it appear to vary by class size? And the answer is sort of. That typically a p-value cutoff you use is 0.05. In this case, we would fail to reject the null hypothesis that gender and class size are unrelated. But it's getting pretty close to statistical significance. Typically, the cutoffs people like to use are 0.01, 0.05, and 0.1. I would still say we failed to reject it, but a lot of folks would at least sort of acknowledge that you're getting close. But I would not recommend that necessarily. What is the distribution of household incomes? Does it appear to vary by class size? So there are a few different ways you could have done this. The thing that I actually like more than anything is just still visualization. And what I did here was I did something called faceting, which basically tells data that I want to plot the histogram and do it by class size. And we can see a pretty clear relationship that as you get to a smaller class size, the center of mass of each of these distributions seems to move to the right, so that a small class size on average seems to have higher household income than either a medium or a large household. But because of that sort of multiple comparison problem, there are a couple of different ways we could test that. And so we will use the regress command and this class size code. And there are a couple of things that you can look at when you're saying, is there a relationship between household income and class size? You can note that these questions of, is there a statistically significant difference between, say, a large, small, and a median class size on an individual basis. But the nice thing about regression is it also gives us the associated F statistic and the p-value associated with that F statistic. And here we see that it's less than a threshold of 0.05. So we would reject the null hypothesis that household income and class size are unrelated. And just to reiterate that, we could do the exact same thing with an ANOVA analysis. And note our R-squareds don't change, our mean squared error doesn't change. And we still have the associated p-value to look at, as well as the same F statistic. But I think the regression framework is what you're going to see most often. So moving on, we're going to go to the next question about the distribution of test scores and do they appear to vary by class size. We're going to run all three analyses again, and let's take a look at what that graph looks like. Oh, I plotted the wrong thing. It's not household income. So it's not quite as clear of a contrast, but there does seem to be that tendency that for math scores, there does seem to be some difference between the center of mass being further to the right for small and medium relative to large. And let's take a look at what is going on for reading. Do we see a big difference there? I cannot honestly remember. Let's relabel those plots just to be clear. Math score, we can see that as class size increases, it appears, at least visually to me, that that smaller class size is associated with higher test scores. Let's see if we can see that same relationship in reading. And in reading, it's really hard to tell for me. I'm not seeing any big shifts in distributions, but sometimes, particularly when you have these sorts of coarse binnings, it's not necessarily obvious because the center of mass might be different. But at least for me, it seems like maybe the distribution is a little bit tighter for small test scores. But for the most part, the center of mass still seems to be in the same approximate range. But the great thing about this is we have ways to test this more formally. And so the first thing we do is we ask you to test large versus small class sizes by math scores. And we can do this as a t-test. And my if statement here is basically telling to test the difference between class sizes for all cases where class size is not equal to medium. In this case, because we only have three categories, that's going to be small or large. We run our ANOVA to see if there's any difference. We see that there's clearly a difference between small and large classes. The difference is on the order of 20 points. Let's see if that varies with class size. Again, we run our regression. Here we see our associated math score for large class sizes, and for small and medium, we need to add them up. So small class sizes get a score of about 120, 119. Medium class sizes get a score closer to 110. The next thing that we do is we add in additional information about the student. In addition to their class size, we incorporate their household income. And the statistical test that I asked you to think about is, what is the associated coefficient on household income? What is the relationship? And is it statistically significant? And what my interpretation of this coefficient is that conditional on knowing class size, that on average, for each increase in about $1,000 of income, household income should, for each $1,000 increase in household income, a student's math score should rise by approximately 0.1 scale points on the exam. And again, the neat thing is, now that you know this predict trick, we can actually see how this varies across relationships. So let's use this predict option is just letting us know what these model estimates look like. Another neat little trick is we can just look at particular variables. So we only need score math, class size, and household income. Let's look at these three. Sorry, one more. We also need household income prediction. And so we can see that compared to the prior analysis where we only had three unique values because we only had three predictors, the small, medium, or large class size, when we have this continuous outcome, we see many more values because it's a combined function of all of these, not only your class size, but your household income. And as you can see, that looking within, say, a medium household with a difference of about $22,000 of income, our prediction varies by about 2.5 points or so, which is consistent with our coefficients prediction. But it's also worth noting that the reality of these predictions are not necessarily that they're that useful. So for instance, in this case, this particular student got a score of 103 on his math test, but our predicted model was set 113. And this individual got a score of 120, but our predicted model only got a score of about 110. And one of the things that's also worth looking at is this fit statistic that we're only explaining about 22% of the variance in this data. So our model is still missing out quite a bit. So while we do have an F-test that suggests we have at least some significant coefficients in the model, there's still a lot of variation we've yet to explain. The other thing that I think is sort of nice about this type of analysis is that you can think of the models we're generating as sort of predicting the same line with different intercepts for each of these three groups. And if we add in gender as a covariate, what happens? Well, we're still making an individual prediction. We're still making individual predictions, but it's becoming a little bit more bespoke. And what that means is that there will be even more variation, and that the interpretation of our regression coefficients also change. That instead of when all of these coefficients are turned off and we are just looking at our constant, the interpretation of it is no longer what is the score for a student in a large class size. It is now what is the score for a female student in a large class. And so we have to go through these equations individually and sort of ask what is the associated value for each student. And if these covariates are turned on in the sense that it's a medium class size or it's a small class size, or if it's a household income of say $100,000, we need to sort of go through and do that multiplication explicitly. And we can do the same exact analysis for reading scores, and we see largely the same result. I'm sorry, we see the same set of coefficients. However, in this case, we see that the F statistic is much smaller. And while we still would reject the hypothesis that none of these coefficients that all of these coefficients are zero, it's a much smaller amount of variation that we're explaining. And the adjusted R squared is also lower, which is another metric we'll talk more about next week. But in terms of the interpretation of these coefficients, the things you always want to look at are for T, for the associated p-values of statistics, as well as does the confidence interval contain zero. So in this case, we would say the coefficient on gender, whether or not you're a male student, is statistically significant for predicting your reading score. Or there's a statistically significant difference between these two populations after conditioning on all of these things. Now, doing this math and calculation by hand can be quite tricky. So I want to teach you a little bit of a trick to explicitly do these calculations that I asked you to do. So whenever you run a regression, implicitly, all of these values are stored as something called a list. And the way you can access it is you can see all of these parameters and you can sort of see how they map to things in this reported table, as well as the command line used to generate it. And if you want to access, say, these individual coefficients, these are referred to as beta as a shorthand. We can list them explicitly. So we can type in, say, matrix list BB. And one of the things that's kind of tricky about it is it's hard to read necessarily. Is this medium, large, small class size? Or is this, or actually, I think this is class size code and the associated values. So one thing that I tend to do is just run this snippet of code so I can actually see what the full variable names are a little bit more easily. So all I'm doing here is creating a matrix called B that contains these estimated beta coefficients. I do something called transposing this matrix, which all we're doing is instead of making it these column names, we're going to make them row names so they're a little bit easier to read. And when we make them easier to read, we're also going to lengthen the associated columns so we can easily access these coefficients. And so once you've trained your model, you have all of these reference coefficients that you can explicitly access. And one thing that I also want to highlight is the interpretation of these coefficients are a little bit easier to understand. These dot B indicators let you know that this is a base or reference case, and so implicitly that they are going to map to 0. And that's sort of the nomenclature that we use. We'll talk a little bit more about it next week as to why we use this description and language to interpret regression coefficients, but I don't want to overwhelm you too much right now. But what you should take away is that you don't have to do this stuff by hand. That you can access an associated coefficient and its value using this underscore B, and then in brackets, referencing the variable of interest. So in this case, the question is asking, what is the household income of what is the predicted score for an individual who has a household income of 50,000, is male, and is in a small class size? Well, first we need to add that constant value. Then we need to grab the associated coefficient of a small class size. In this case, that's going to be 3.classSize code. Then we need to predict what the associated coefficient is on a household income. That's 50,000. And then finally, we need to add in the coefficient associated with a male student. And what I want you to notice is when we do the same exercise for median class size, let's look at what changes. That all we changed was this class size code of 3 is now 2, because that corresponds to the indicator for median. And when we go and do that same exercise for a large class size, we don't include any class size code underscore beta coefficient. We could, but it wouldn't be necessary to use this 1B class size code because we know that it's been explicitly set to 0 as a reference. And when we do the same thing for, say, a female household income of 100,000, note what changes. We, instead of 50,000, we use 100,000. We still have our constant and our class size for a small class size, but we don't include this gender code variable because implicitly, again, we're using 0 as a reference. I'm going to stop here because the next set of exercises are largely the same, but I'm happy to answer any questions. The one other thing that I wanted to highlight, as we're going to get into it more next week, is we can measure the performance not only via the predicted values, but by also generating things called residuals. And the way you do that is just using this residual option. And one of the neat things about your residuals is that on average, your residuals are going to be equal to 0 if you evaluate them on the same set of data. We'll talk more about these properties next week. Thank you so much, and I hope you have a wonderful day.